lecture for Chapter 13, and the chapter title is about liquids and solids, but our main focus for this chapter is actually intermolecular forces. So before we jump into what those are, we're going to kind of go back to stuff we used last chapter. Normally we do Chapter 12 after Chapter 11, and it's about gases. But then we come back to Chapter 13, and you have to remember all that stuff from Chapter 11, so we're doing it a little bit different order, and we'll do gases when we come back from spring break, and Mr. Huddleston's going to teach that chapter. So, background stuff you need to know going into this. We need to talk about bond polarity. So, we've been talking about electronegativity for a couple of chapters now. Alright? Remember, that is how much a particular atom pulls on the electrons in a bond. And the more electronegative you are, the more you pull on those electrons. So we can actually quantify this and call it bond polarity. If you remember the investigation we did with periodic trends, if you had electronegativity, there were actually numbers for that. So if you simply take the difference between the electronegativity values between two atoms that are bonded, you can figure out sort of what kind of bond it is, okay? Because up to this point, we've only talked about covalent and ionic. Well, there's sort of an in-between called polar covalent, and that just means that the electrons are not shared equally between the two atoms, okay? So if you need to look them up in your book, they're on page 320. The cutoff numbers between polar covalent and ionic vary depending on who referenced them, but these are the ones that I see most often, so I use these. So you can just kind of remember if it's below 0.4 or 2 or greater, then it's the extremes. Everything in between is polar covalent. So why do we care about this? What the electrons are doing, as we've seen this theme, determines a whole lot of stuff about the chemical behavior of atoms and molecules. Okay, so we care about where the electron's residing most of the time because it has an effect on how the molecules behave. So the covalent ones that you see tend to be like they're diatomic molecules. Of course, there would be no difference between their electronegativity, so they share the electrons completely equally. And then the least electronegative nonmetal elements, polar covalent qualifies most of what you see as covalent bonds between two nonmetals. And then, of course, ionic, easy to see that, metal and a nonmetal. And I've got some examples on the next slide that you don't have to write down, but just to show you what we're talking about. Alright, so here are some examples of using those electronegativity values to determine what type of bond there is. So you see the top, hydrogen, it's a diatomic molecule. They have the exact same electronegativity, so it's a completely covalent bond where they share totally equally. And then the next three, you know, you would look at that and say, yeah, that's a covalent bond because it's two nonmetals. But you see that the electrons are not shared equally. It's polar covalent. And then that last one, metal-nonmetal, which you would predict to be ionic. And it is. It's got a difference of 2. There's actually, I've seen some publishers that stop polar covalent at like 1.8, so they say that fluorine and hydrogen's an ionic bond. I'm like, hydrofluoric acid actually does dissociate in water to form ions, but it doesn't dissociate completely, so I guess that's where that it's right there on the cusp of being ionic. So, you're not actually going to have to like know these values or anything. If I asked you to do this on the test, I would have to give you the values, and then you would just have to know to take the difference, but you would need to know where, you know, the ranges are. When we get closer to the test, I'll tell you whether or not we got to get it, because I really cannot remember if I put that on the test or not. Okay? Alright, so why do we care about this, whether or not bonds are polar or nonpolar? Because it has an effect on the overall molecule. Okay? If you've got polar bonds, it can create the situation where the molecule is said to have a dipole moment. I feel like dipole is an oxymoron because if you're polar, it means you've got two ends, and dipole is saying two poles. Again, yeah. So anyway, what happens, you see in the diagram, is that you end up with a molecule that has an area that has a slightly positive charge and an area that's slightly negative due to the electrons spending most of their time with one atom versus another one. So the picture there's three different representations. The one on the far left that says, water to the left of it, if you see the odd-looking squiggles, those squiggles are actually the lowercase Greek letter delta, kind of like the Greek lowercase d. And that is the symbol that in science we use to indicate a partial charge. And it has to have a plus sign or a minus sign out to it. So if you're looking at that, you see that there's a partial positive charge in the area where your two hydrogens are. And it's a little bit harder to see, but there's the symbol for a partial negative charge at the bottom of your red oxygen atom. Because most of the time the electrons that are shared between them spend more time on the oxygen. Okay? The middle representation that says bond dipoles is a way of showing the direction of the electron pull. Notice that the end of the arrow sort of looks like a plus sign or a cross because it always points from the positive area to the negative area. And then the last one is showing the net dipole. Overall, the molecule has negative side where the oxygen is and positive side where the hydrogens are. Now, application of this will come a little bit later. It's going to be more of you saying, okay, this is a polar bond or a nonpolar bond. If it's a polar bond, which of the two has a greater electronegativity? The arrow is going to point towards that one. And you're going to need to know that to evaluate whether or not a molecule overall is polar or nonpolar, which should be the next thing on the next slide. Alright, we good? Alright, so we call a molecule polar if it has that net dipole moment. If it doesn't, it's nonpolar. So how do you end up with polar or nonpolar? I sort of repeat a little bit of the middle paragraph on the next slide. But it is possible to be a nonpolar molecule with polar bonds. What happens is that the symmetry of the structure, you remember a lot of the molecular geometry structures were very symmetrical. You can have that situation where the bonds sort of cancel each other out, and then you end up with an overall nonpolar molecule. So no particular area positive or negative. Okay. Why do we care about that? Chemical behavior, one of the things that it affects the most is solubility. If you've ever wondered why oil and water do not mix, it's because of their polarities. Okay, we use the phrase like dissolves like, and it's talking about the polarity. So polar stuff dissolves in polar stuff. Non-polar stuff dissolves in non-polar stuff. So like salt is ionic compound. And so, therefore, it's got a very polar bond. And it dissolves in water because water's polar. Okay? But if you've ever tried it, salt will not dissolve in oil. Okay? Because oil is nonpolar. And that's also why oil and water will not mix. You can shake it and shake it and shake it and get them to be temporarily interspersed. But the oil and water will always separate because of their polarities. They simply will not dissolve in each other. So, if you've got an oily stain on your clothes, simply rinsing it with water is not going to get it out. you would actually do better with using like some alcohol. This alcohol is an odd molecule that has a polar end that allows it to dissolve in water to a certain extent, and so that's why it can do both things. So for those of you watching at home, I just gave the life tip to the class in here that ink is a non-polar thing, but alcohol sort of has this dual personality. So if you ever get ink or Sharpie on your clothes, use alcohol with lots of cotton balls to blot it to get it to come out. Okay, so how do you tell if something is polar or non-polar? Here's more of your like concrete criteria, because one of the things you're going to have to do is look at, I'm going to give you a formula, and you're going to have to figure out, is this a polar or non-polar molecule? And that's why you have to be able to draw the Lewis structure and know the shape of it, because we know certain shapes give us non-polar molecules even if it contains polar bonds. Okay? So it is possible to have just a non-polar molecule like the diatomic elements, completely non-polar. But you could have something that has one of those 6 shapes: linear, trigonal planar, tetrahedral, octahedral, trigonal bipyramidal, and square planar. As long as all of the atoms bonded to the central atom are the same, then because of the geometry, it's a nonpolar molecule. And there's some examples that are written up there. You don't have to have those like memorized, but on a test, if I gave you those formulas, you should be able to draw the structure, know the shape, and say, okay, this is polar or this is nonpolar. Okay. Okay. So the polar stuff, of course, if it's only a binary compound and it's not diatomic, it's pretty much going to be polar. But the asymmetrical shapes, even if all the bonded atoms are identical, if it's an asymmetrical shape, the dipoles do not cancel. So, like bent is always a polar shape. The pyramidals, like trigonal pyramidal, is going to be polar. The square pyramidal will also be polar. Trigonal bipyramidal, though, is not, because they're all completely balanced. Like the 3 that are on the XY plane balance each other exactly, and then the 2 that are along the z-axis balance each other. So there's some examples there. Why do we need to know if it's polar or non-polar besides what's going to dissolve in what? Well, it determines what kind of forces of attraction are between the molecules themselves. And we care about that because it determines what state of matter things are. If you ever wondered why are some things solid, why are some things liquid, why are some things gases? It has to do with the forces between the molecules. Alright, so on to the application of that stuff. There are lots and lots of different forces going on inside molecules and atoms and outside of them. So intramolecular forces are the ones inside the molecule. It's what holds the molecule together. So that would be like covalent or ionic bonds. But there's also intermolecular forces that we abbreviate IMF that are between 2 different molecules. Okay? So, as far as like a force of attraction, they're much, much weaker than like the ionic or covalent bond. But they're important because they are what determine whether something is a solid, liquid, or a gas. Okay, and we'll talk about in a little bit, like, why is it the group 17 elements have 2 gases, a liquid, and some solids. It also determines how much energy we have to put into a substance or remove from a substance to cause it to go through a phase change. So like, if you have water at 100 degrees Celsius, you have to put a little bit of extra energy into it to overcome the intermolecular forces to make it boil and become a gas. And And likewise, if you're going from like liquid to solid, water at 0 degrees Celsius has to lose a certain amount of energy to freeze, because that energy keeps the intermolecular forces from overcoming and making it go into a certain phase. And we'll talk about that in more detail, but that's why this stuff is so important. There are actually 7 different intermolecular forces, but we're only going to talk about 3. All right, so the first one we're going to talk about is London dispersion forces. And sometimes they just call them dispersion forces, but I like calling them London dispersion forces because then it's easier to abbreviate it LDF. And that's what we usually end up calling it. But, and we're going from weakest to strongest of the 3. So this exists for all species, okay, well, except for hydrogen ions because they don't have any electrons. But this is important because if you are a nonpolar molecule, this is the only force of attraction from one molecule to the next. Okay? So, if there was no such thing as London dispersion forces, everything that's nonpolar would exist in a gaseous state. Always. So, the reason why nonpolar things that are liquids and solids is because of their intermolecular forces, those London dispersion forces. And they, excuse me, need to know it's the weakest one. And also, when one of the things you're going to have to do is compare forces between molecules. So if you're trying to decide which of the 2 nonpolar things has greater London dispersion forces, it's the one that's larger. Because as the size of the atoms and molecules increases, they get more and more electrons, and that means they have greater and greater LDF. So the biggest example of this that you need to remember as a specific example about this is the group 17 elements, our most colorful group in the periodic table. Because we've got fluorine and chlorine, 2 gases that are in red. Then we have bromine, one of the only 2 liquids in blue on the periodic table. And then iodine and acetine, which are both solids. And we don't usually talk about acetine too much because it's very rare and radioactive. So if we talk about the big 4, though, that we see all the time, as they get larger going down the group, you go from gas to liquid to solid, because there's increasing attraction between the molecules themselves. Because the greater the attraction is from one molecule to another, the more ordered the state of matter is. And if you remember way back to, how much things move around in the solid state versus the liquid and gaseous state, solids are pretty much vibrating in place. Liquids are a little bit freer to slip and slide past each other, and then gases have little to no attraction for each other, and they're just bouncing around all over the place. So that is why you see what you see. Now, where do the forces themselves come from? Okay, like, why is it that the bigger it gets, the greater the force there is? Okay, has to do with what the electrons are doing. Alright, so think about electrons for an atom, and in, also plus molecules. They're, in their orbitals, where they are found 90% of the time. But do you think at any given moment that all of the electrons in an atom or a molecule are distributed exactly evenly? Are they like that all the time? Or do you think it's possible that the electrons may be mostly on one side or the other? What do you think? Are they always distributed evenly or no? No, they are not, because the electrons are moving. So, at any instant, a molecule could be a dipole because the electrons are crowded to one side, making that side negative and the other side by default positive. So the larger you are and the more electrons you have, the greater the force is that comes from this. Because all of these forces you're going to see come from this attraction of positive parts to negative parts. So it's like an instantaneous dipole, and the larger, more polarizable you are, the more electrons you have, the more often this happens, and so there's greater and greater forces at any given moment. And that's why you see bromine becoming a liquid, iodine being a solid. Okay? So that was the weakest force. Now, stronger force, but not the strongest of the three we're looking at, is dipole-dipole forces. And this is literally the opposite charges attracting each other. So this exists only for polar molecules. Nonpolar molecules don't have this. The only thing nonpolar has is LDF. So polar molecules have LDF and this. Okay? And it's literally, if you just think of the molecules as sort of being like little magnets, the opposite ends are going to attract each other. And you see again in the diagram, the symbol for partial charges, the lowercase Greek letter delta that looks like a squiggle. You see that the positive side of one molecule is attracting the negative side of another one. Okay. And a little bit harder to see from the back, but something to notice is that whenever you draw diagrams of these things, covalent and ionic bonds are drawn with a solid line. Intermolecular forces, like London dispersion forces or dipole-dipole forces, are drawn with a dashed line to show the difference. So if it's a solid line, it's all part of the same molecule. If it's a dashed line, it's attraction between one molecule and another molecule. All right, the last force, the third one, the strongest one, is hydrogen bonding. And it's pretty much a supercharged dipole-dipole force. But it's so much stronger than any other dipole-dipole force that it gets its own special name. And don't be confused thinking that since it's called hydrogen bonding, it's bonding between hydrogens. It's not. Okay? It's called hydrogen bonding because the molecule has to have hydrogen bonded to one of three specific elements: nitrogen, oxygen, or fluorine. And because those three things are so very polar, and hydrogen, they're very electronegative, and hydrogen is very not, you get a super, super polar bond that's very positive on the hydrogen side and very negative on the other side. So it's just like dipole-dipole that the opposite ends are attracting, but it's just stronger. So again, boiling points are very important. Okay, why does water have such a high boiling point? It's because of this. And there's a diagram, again, showing you the dashed lines between water molecules, showing their intermolecular forces. So that would be the hydrogen bonding. It's literally hydrogen bonding to the negative thing. And then the chart shows you how much higher the boiling point is of things that experience hydrogen bonding versus what would be expected, because generally boiling point increases with increasing mass, but you see water, which is so much smaller than those things, has such a high boiling point. It's because of the hydrogen bonding. And that is it.